LLM2Vec, large language models are secretly powerful text encoders. Parashad Banam Gade, Vaibhav Adlakha, Marius Mosbach, Dmitry Badanow, Nicholas Chapados, Siva Reddy. Abstract, large decoder-only language models, LLMs, are the state-of-the-art models on most of today's NLP tasks and benchmarks. Yet the community is only slowly adopting these models for text embedding tasks, which require rich contextualized representations. In this work, we introduce LLM2Vec, a simple, unsupervised approach that can transform any decoder-only LLM into a strong text encoder. LLM2Vec consists of 3 simple steps. 1. Enabling bidirectional attention. 2. Masked next token prediction. And 3. Unsupervised contrastive learning. We demonstrate the effectiveness of LLM2Vec by applying it to 3 popular LLMs ranging from 1.3b to 7b parameters and evaluate the transformed models on English word and sequence-level tasks. We outperform encoder-only models by a large margin on word-level tasks and reach a new unsupervised state-of-the-art performance on the Massive Text Embeddings Benchmark, MTEB. Moreover, when combining LLM2Vec with supervised contrastive learning, we achieve state-of-the-art performance on MTEB among models that train only on publicly available data. Our strong empirical results and extensive analysis demonstrate that LLMs can be effectively transformed into universal text encoders in a parameter-efficient manner without the need for expensive adaptation or synthetic GPT-4 generated data. 1. Introduction. Text embedding models aim to encode the semantic content of natural language text in vector representations, which then facilitate various natural language processing (NLP) tasks, such as semantic textual similarity, information retrieval, and clustering. For many years, the dominating paradigm for building such models relied on pre-trained bidirectional encoders or encoder-decoders such as BERT and T5, which are typically adapted for text embedding tasks by following a multi-step training pipeline consisting of weekly and fully supervised contrastive training, Nye et al. 2022, Li et al. 2023, Xiao et al. 2023, inter alia. Only recently, the community started to adopt decoder-only LLMs for embedding text. We speculate that the slow adoption of decoder-only LLMs for text embedding tasks is partly due to their causal attention mechanism, which inherently limits their ability to produce rich contextualized representations. At any given layer, causal attention limits token interactions, ensuring that the representation of a token at position I is influenced solely by the representations of preceding tokens at position 0, 1, I, -1. Although this limitation is necessary for generative capabilities, it is suboptimal for text embeddings as it prevents the representations from capturing information across the entire input sequence. Figure 1. The 3 steps of LLM2Vec. First, we enable bidirectional attention to overcome the restrictions of causal attention, BI. Second, we adapt the model to use bidirectional attention by masked next token prediction training, MNTP. Third, we apply unsupervised contrastive learning with mean pooling to learn better sequence representations, SIM-CSE. Overcoming this architectural limitation of decoder-only LLMs for text embedding tasks is highly appealing as these models come with several advantages compared to their encoder-only counterparts. During pre-training, decoder-only LLMs learn from all input tokens and not just a small percentage too, which, given the same amount of training data, makes them much more sample-efficient than encoder-only models. Moreover, there exists a rich ecosystem around these models, with extensive tooling and well-tested pre-training recipes, which has resulted in continuous improvement of these models by the community. Lastly, recent work on instruction fine-tuning and learning from human preferences has resulted in decoder-only LLMs that excel at instruction following, making them an ideal choice for building universal text embedding models that generalize across a large variety of tasks using instructions. In this work, we provide a simple unsupervised approach, termed LLM2Vec, which can be used to transform any pre-trained decoder-only LLM into a universal text encoder. As shown in Figure 1, LLM2Vec consists of 3 simple steps. 1. Enabling bidirectional attention. 2. Masked next token prediction. And 3. Unsupervised contrastive learning. Crucially, LLM2Vec does not require any labeled data and is highly data and parameter efficient. We apply LLM2Vec to 3 decoder-only LMs ranging from 1.3b to 7B parameters, SLM1.3B, LLM2Vec, and Mistral 7B, and evaluate the resulting models on word and sequence level tasks. On word level tasks, chunking, named entity recognition, and part of speech tagging, LLM2Vec transformed models outperform strong encoder-only models by a large margin, demonstrating its effectiveness for producing rich contextualized token representations. On the massive text embeddings benchmark, LLM2Vec transformed models set a new state-of-the-art for unsupervised models, with our best model reaching a score of 56.8. Additionally, we combine LLM2Vec with supervised contrastive training and achieve a new state-of-the-art performance among models that train only on publicly available data. Beyond our strong empirical results, we provide an extensive analysis of how LLM2Vec affects the representations of the underlying model and reveal an intriguing property of Mistral 7B, the currently best-performing architecture on MTB. Overall, our work demonstrates that decoder-only LLMs are indeed capable of producing universal text embeddings, and only very little adaptation is required to reveal this ability. Our code and pre-trained models are at github.com/LLM2Vec. 2. LLM2Vec 2.1. 3 simple ingredients. Enabling bidirectional attention, BI. The first step of the LLM2Vec approach is to replace the causal attention mask of decoder-only LLMs by an all-ones matrix, see Appendix B.1, for background on the self-attention mechanism. This gives each token access to every other token in the sequence, converting it into a bidirectional LM. However, it is not a priori clear why this should lead to better sequence representations. After all, the decoder-only LLM was not trained to attend to future tokens, and therefore, this naive approach might even lead to worse representations. As we show, simply enabling bidirectional attention does indeed decrease embedding performance for most models. We can, however, easily adapt a model to make use of its bidirectional attention. Masked Next Token Prediction, MNTP. We propose a simple strategy to make the model aware of its bidirectional attention by adapting it via Masked Next Token Prediction, MNT. MNTP is a novel training objective that combines next token prediction with masked language modeling. Given an arbitrary sequence x, x1, x2, xn as input, we first mask a fraction of the input tokens and then train the model to predict the masked tokens based on the past and future context. Crucially, when predicting a masked token at position I, we compute the loss based on the logits obtained from the token representation at the previous position I-1, not the masked position itself, see Figure 1. Unsupervised contrastive learning, SIM-CSE. While the previous 2 steps of the LLM2Vec recipe can transform any decoder-only LLM into an encoder for word-level tasks, they might not be sufficient for sequence representations. Unlike bidirectional encoders that include a next sentence prediction objective in their pre-training objectives, decoder-only LLMs are not explicitly trained to capture the context of the entire sequence. To fill this gap, we apply unsupervised contrastive learning via SIM-CSE. Specifically, given an input sequence, it is passed through the model twice with independently sampled dropout masks, resulting in 2 different representations for the same sequence. The model is trained to maximize the similarity between these 2 representations while minimizing the similarity with representations of other sequence in the batch. Crucially, this step does not require any paired data and can be applied using any collection of sequences. We use a pooling operation on the token representations to get the sequence representation, more details in section 3.2. The 3 steps combined, BI plus MNTP plus SIM-CSE, constitute the LLM2Vec recipe. 2.2 Transforming decoder-only LLMs with LLM2Vec models. We experiment with 3 different decoder-only LLMs ranging from 1.3B to 7B parameters: Sheared Lemma 1.3B, Llama 2 7B Chat, and Mistral 7B Instruct v.2. Training data: we perform both the MNTP and the unsupervised SIM-CSE step using data from English Wikipedia. We select data from Wikipedia as it was included in the pre-training mixture of all the models we experiment with. It is therefore fair to assume that these 2 adaptation steps are not teaching the model any new knowledge beyond how to attend to future tokens and how to construct sequence representations. Specifically, we use the Wikitext 103 dataset for the MNTP step and a subset of Wikipedia sentences released by Gao et al. 2021. For the unsupervised SimCSE step, masked next token prediction. We follow established practice from the masked language modeling literature and randomly mask a fraction of the tokens from the input sequence. We use the underscore as the mask token since the models we experiment with do not have a special token for masking. We fine-tune the model using LoRa to predict the masked token using the representation of the previous token to maximally align our training objective with the pre-training setup of decoder-only LLMs. Figure 2. Evaluation of LLM2Vec transformed models on word-level tasks. Solid and dashed horizontal lines show the performance of Uni and Deberta v3 large, respectively. For all models, we trained for 1,000 steps with a batch size of 32 on a single 80GB A100 GPU. For 7B models, this training takes only 90 minutes. We provide additional details of our training setup and hyperparameters in Appendix D.1. Unsupervised contrastive learning. For the contrastive training, we apply the unsupervised SimCSE approach by Gao et al. 2021. The positive examples are constructed by applying the LLM's dropout twice on the same input sequence, whereas other sequences in the batch act as in-batch negatives. We merge the MNTP LoRa weights into the base model and initialize new LoRa parameters before starting the SimCS training, which ensures that the model retains the knowledge learned in the previous step. Similar to the MNTP step, we train for 1,000 steps. For 7B models, this training takes 2.5 hours on a single 80GB A100 GPU with a batch size of 128. We provide additional details of our training setup and hyperparameters in Appendix D.1.2. 3. LLM2Vec transformed models are strong unsupervised text embedders. 3.1. Evaluation on word-level tasks. We start by evaluating on word-level tasks to demonstrate that LLM2Vec is successful at improving the contextual representations constructed by decoder-only LLMs. Setup. We evaluate on 3 word-level tasks: chunking, named entity recognition, NER, and part-of-speech tagging, POS, using the Cohen LL2003 benchmark. We embed each input sentence and train a task-specific linear classifier on top of the frozen representations. This is akin to the linear probing setup commonly used in the language model analysis literature. We compare the LLM2Vec transformed models to Deberta v3 large, the current state-of-the-art encoder-only model. Additional details about our setup are provided in Appendix D.1.3. Results Figure 2 shows the results of our evaluation. A detailed breakdown of the results is provided in Table 4. On each of the 3 tasks, constructing token representations, with causal attention, Uni, already outperforms the encoder-only baseline. This is not surprising, given that the models we experiment with are significantly larger and have been pre-trained on more data. As expected, naively applying bidirectional attention dramatically hurts performance in most cases. Interestingly, for Mistral 7B, enabling bidirectional attention hurts performance much less compared to Ella 1.3b and Llama 2 7b. For NER, Mistral's performance even improves by 0.6% with bidirectional connections. Next, we observe that for all models and tasks, further adapting via MNTP, i.e. LLM2Vec SimCSE, improves performance. For instance, in the chunking task, we see improvements for Llama 1.3b by 5%, Llama 2 7b by 4%, and Mistral 7b by 4%. Finally, combining MNTP with SimCSE, however, performs worse than just applying MNTP. This is expected for word-level tasks, as SimCSE adapts the representations for sequence-level tasks. Figure 3. Unsupervised results on our 15-task subset of the MTB dataset. We ablate 3 different pooling choices: EOS mean pooling and weighted mean pooling. LLM2Vec is compatible with all 3 approaches and works best with mean pooling. Table 1. Unsupervised results on MTB. We compare Llama 1.3b, Llama 2 7b, and Mistral 7b with and without LLM2Vec to the unsupervised BERT models of Gao et al. 2021, as well as echo embeddings. 3.2. Evaluation on sequence-level tasks. Next, we evaluate on the Massive Text Embedding Benchmark, a collection of 7 diverse embedding task categories covering a total of 56 datasets. To select the best-performing pooling method for each method, we perform ablations on a 15-task subset consisting of representative tasks from each of the IB categories. We provide additional details and justification for how we chose this subset in Appendix C.1. Setup. Following previous work, we evaluate with task-specific instructions. We use the same instructions as Wang et al. 2023 and only add instructions to queries. The instructions can be found in Table 10. For symmetric tasks, the same instruction will be used for the query and the document. When applying weighted mean pooling, we exclude the instruction tokens. As a baseline, we compare to the unsupervised BERT models obtained from Gao et al. 2021. Additionally, we compare to echo embeddings, a concurrent approach by Springer et al. 2024, which we run with the same models and instructions. See Appendix E.1 for more MUT. Figure 4. Cosine similarity between query Q and negative S- as well as positive examples S+. Plots for LLM2Vec and other approaches are shown in Appendix F. Details on our implementation of echo embeddings. Echo duplicates the input and pools only over the second occurrence to address the limitation of causal attention. Results on our 15-task subset of MT Figure 3 shows the impact of various pooling methods for all three models on the subset of MT tasks. We can clearly observe that applying causal attention is suboptimal when constructing text embeddings. The naive approach of applying the EOS pooling for models with causal attention is outperformed by weighted mean pooling. Enabling bidirectional attention without any training harms performance for LLM1.3b and LLM2Vec. Similar to our word-level results, the performance of Mistral 7b improves with bidirectional attention, even without any training. For LLM2Vec transformed models, applying MNTP training improves the performance of SLMA 1.3b and Mistral 7b. Moreover, applying SimCSE further boosts the performance of SLMA 1.3b, LLM2.7b, and Mistral 7b by 49.8%, 20.2%, and 37.5% compared to the best causal baseline on the MTEB subset. We conduct further ablations of each component of the LLM2Vec recipe in Appendix D.2, Table 5. Results on full MT Table 1 shows the results of the best performing models, which we select based on the ablation above, on the full MTB dataset. After the first two steps of LLM2Vec, bidirectional attention and MNTP, LM2Vec WO SimCSE, we observe a considerable improvement in performance for all three models, e.g. 16.4% improvement for Mistral 7b. When comparing to echo embeddings, LM2Vec OSIMCS3 leads to improved performance for SLM1.3b and LM2.7b and performs almost on par for Mistral 7b. However, compared to echo embeddings, LLM2Vec is much more efficient as echo embeddings repeat the input and therefore double the sequence length, which makes inference considerably slower. We provide a runtime comparison in Appendix E.2. Adding the final step of the LLM2Vec recipe, unsupervised SimCSE, further boosts all three models by a large margin, making our LLM2Vec Mistral 7b state-of-the-art among all unsupervised models with a score of 56.82. Overall, our results highlight that LLM2Vec is successful at transforming decoder-only LLMs into strong text embedding models that outperform previous unsupervised approaches on the challenging MTEB leaderboard. 4. Does LLM2Vec affect a model? 4.1 LLM2Vec helps models to capture information from future tokens. To analyze the extent to which LLM2Vec transformed models incorporate information from future tokens, we adopt the analysis of Springer et al. 2024 and test how good models are at judging the similarity of sentences that have different meanings but share the same prefix. We only directly compare the performance after the first two steps of LLM2Vec to echo embeddings, as applying SimCSE involves learning sequence representation, which makes the comparison unfair. Figure 5. Cosine similarities at different token positions at layers when comparing representations constructed with causal attention to those constructed with bidirectional attention without training. Additional plots are shown in Appendix F. Setup: we evaluate on a synthetic dataset collected by Springer et al. 2024, which consists of 35 sentence triples QI, S plus I, S minus I, third equals 1 with QI equals AI, BI, S plus I equals AI, CI, and S minus I equals AI, DI, where BI and CI have a similar meaning to each other, but BI and DI don't. We compute a sequence representation for each of these sentences by pooling only over the first part of the sentence, i.e. AI. We then compute the cosine similarity between the resulting embeddings. A model that incorporates information from future tokens, BI, CI, or DI, in the representations of the prefix AI should assign a higher similarity to the positive example. Results Figure 4 shows the results of our analysis for LLM 1.3b and Mistral 7b. Results for LLM2Vec, which show the same trends and a comparison to echo embeddings, are provided in Appendix F. For LLM 1.3b, we observe that enabling bidirectional attention and training with the MNTP objective are sufficient to establish a clear separation between the positive and negative examples. For Mistral 7b, all setups lead to a larger cosine similarity between the query and positive than the query and negative examples. 4.2. Why does bidirectional attention without training work for Mistral models? Our empirical results so far, as well as the analysis above, share an intriguing observation. Enabling bidirectional attention works well for Mistral 7b, even without any training. Below, we investigate this surprising behavior by analyzing how bidirectional attention impacts the representations of a model. Setup. We feed a single input sequence, a random paragraph from Wikipedia, to each model and compute the hidden representations of every token at every layer L with causal HCl and bidirectional attention HBIL. For every layer, we compute the cosine similarity between the representations constructed using causal and bidirectional attention, i.e. sim HCl HBIL. For most layers, we expect this similarity to be low, as enabling bidirectional attention without any training should lead to substantially different representations. Results Figure 5 shows that, as expected, for LLM 1.3b and LLM 2.7b, enabling bidirectional attention without training has a profound impact on the representations, leading to low cosine similarity across almost all layers and token positions. For Mistral 7b, on the other hand, the representations have very high cosine similarity throughout. Based on these findings, we replicate these results for other inputs and other Mistral models in Appendix F, and the strong unsupervised results for Mistral 7b with bidirectional attention, we speculate that Mistral models are pre-trained with some form bidirectional attention, e.g., prefix language modeling, at least for some parts of its training. We leave a more detailed investigation of this intriguing behavior for future work. Table 2. Supervised results on full-M benchmark. The best-performing LLM2Vec model achieves a new SOTA performance among models trained only on publicly available data. Figure 6. Results on the 15-task subset of MTB during training. For all three models, applying LLM2Vec before supervised training leads to better performance with fewer steps. 5. Combining LLM2Vec with supervised contrastive learning. The final piece of our evaluation combines LLM2Vec with supervised contrastive learning. 5.1 LLM2Vec leads to strong performance on the MTEB leaderboard. Setup. For supervised training, we train on a replication of the public portion of the E5 dataset curated by Springer et al., 2024. The dataset consists of approximately 1.5 min samples, and we provide details on its compilation in Appendix G.1. We follow standard practice and train the models with contrastive learning using hard negatives and in-batch negatives. We use LoRa fine-tuning for the supervised setting as well. The MNTP LoRa weights are merged into the base model, and the trainable LoRa weights are initialized with SimCSE weights. For LLM2Vec models that use just MNTP, the LoRa weights are randomly initialized. The training is performed for 1,000 steps with a batch size of 512. We detail other hyperparameters in Appendix G.2. For a fair comparison, we only compare to models trained on publicly available data and provide a comparison to the top entries on the MTEB leaderboard in Appendix G3. Results. Table 2 shows the results of our evaluation. For all three models, transforming a model with LLM2Vec leads to improved performance over the strong uni plus weighted mean baseline. Performing unsupervised SimCSE is less crucial for supervised training and even leads to slightly worse performance for LLM2.7b and Mistral 7b compared to just performing the MNTP step of LLM2Vec. However, as we will show in Section 5.2, LLM2Vec with MNTP and SimC is much more sample efficient and therefore crucial in computer data-constrained settings. Notably, our best model, Mistral 7b, LLVec SimCSE, leads to a new state-of-the-art performance among models trained only on publicly available data. 5.2 LLM2Vec leads to more sample-efficient training. Setup: to demonstrate the sample efficiency of LLM2Vec transformed models, we save a checkpoint every 25 training steps and evaluate them on our 15-task subset of MTEB. Results: as shown in Figure 6, LM2Vec transform models achieve better performance earlier in training. This observation is consistent across all three models. For SLM1.3b, the smallest of our three models, even performing just MNTP leads to considerably improved sample efficiency. These results are particularly encouraging for settings where it is hard to acquire high-quality labeled data, a setting which we leave for future work. 6. Related work. Supervised text encoders. Initially, supervised methods primarily relied on tasks such as natural language inference or sentence similarity to train BERT-like models for producing sentence embeddings. Subsequently, BERT-like models have also been adapted to tasks like retrieval. More recent methods have further improved these models through a complex multi-stage learning pipeline that consists of large-scale weekly supervised contrastive training followed by multitask fine-tuning. Recent approaches have focused on enhancing the generalization and transferability of text embeddings using instructions. Unsupervised text encoders. Another line of work has explored training text embedders in an unsupervised manner using only a set of unordered sentences. These unsupervised approaches typically create two different representations of the same sentence for contrastive learning. The methods vary in how they form these representations, perturbing the input sentence or using different model instances. SimCSE, the approach used in this work, generates two representations of the same sentence by passing it through the model twice with different dropout masks, turning decoder-only LLMs into text encoders. While decoder-only LLMs have outperformed bidirectional encoders across a large variety of language understanding tasks, Brown et al. 2020, Tuvron et al. 2023, Jiang et al. 2023, inter alia, their impact on sentence representation learning remains limited. The most common approaches in the literature use the final hidden state of the last token as the sentence embedding. Very recent and concurrent works address the inherent limitation of LLMs for sentence representation, their causal attention mechanism. Munighoff et al. 2024 perform multitask, full fine-tuning using a combination of self-supervised language modeling with causal attention and supervised contrastive learning with bidirectional attention. In contrast, our proposed approach is much more computationally efficient, as it requires only parameter-efficient fine-tuning and 1,000 gradient steps. Closest to our work is the concurrent work of Springer et al. 2024. They propose copying the input sequence and appending it to itself, which addresses the contextualization issue of causal attention, as tokens in the copy of the input can now attend to future tokens in the previous sequence. While this performs well in practice, it significantly increases the computational cost at inference time, which can be particularly problematic for encoding longer documents. Our approach outperforms Springer et al. 2024 without inducing any additional computational overhead at inference time. 7. Conclusion. We present LLM2Vec, a strong unsupervised approach to transform any decoder-only LLMs into a universal text embedder. We perform an extensive evaluation on word and sequence-level tasks and demonstrate the effectiveness of LLM2Vec in both unsupervised and supervised settings. Applying LLM2Vec to Mistral 7b achieves a new state-of-the-art performance on MTEB among unsupervised approaches, as well as among supervised approaches that train only on publicly available data. Beyond our strong empirical contributions, we provide an extensive analysis of how LLM2Vec impacts the underlying model and reveal an intriguing property of Mistral 7b, which explains its strong out-of-the-box performance with bidirectional attention. The simplicity of our approach, as well as its compute and sample efficiency, makes LLM2Vec a promising solution for low-resource and compute-constrained scenarios and opens up several interesting avenues for future work. Acknowledgements. We thank the members of SR's research group for providing feedback throughout the project. Furthermore, we thank Jacob Mitchell Springer for providing the supervised training data used in Springer et al. 2024. PB is supported by the Mila Intel Grant Program. is partly funded by the Mila P2V5 Technology Maturation Grant and the Mila Samsung Grant. SR is supported by a Facebook CFAR AI Chair and NSERC Discovery Grant Program. This concludes the reading of LLM2Vec, Large Language Models are Secretly Powerful Text Encoders. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.